Dear students, I am Nadeem Khan from J.K College. Today we will discuss about class 11th, chapter number 2, atomic structure. My topic is J.J Thomson cathode rays experiment. It is also called determination of E by M of an electron. E for charge, M for mass. This is also called E by M ratio of an electron. Actually, J.J Thomson in 1898 he took a modified cathode ray tube. Look at this. This is a cathode ray tube. He adjusted a cathode which is connected with the negative terminal of the battery and anode which is connected with the positive terminal of the source battery. So he passed when he applied the high voltage and took the vapors of a gas and this inside this tube and applied high voltage across these terminals. By the application of high voltage, cathode rays were produced. From cathode, there was this is anode. There is a slit, or you can say a small pinhole in the anode. The cathode rays they originated from cathode and passed through the slit and proceeded and strike the point B. Here a fluorescent screen that is represented by the dotted lines. This is the fluorescent screen. This is the fluorescent screen. The property of this fluorescent screen is that when any radiation falls upon it, it produces the fluorescence or glow. So these cathode rays were passed through the slit in anode and strike the point B and produced fluorescence. In absence of any external applied electric or magnetic field. So there was actually initially there was no field, so these cathode rays went straight and strike the point B. Then J.J Thomson applied electric field. You can see this is the anode and this is cathode. When J.J Thomson applied electric field by applying the high voltage at the path of the cathode rays, the cathode rays were deflected towards positive electrode, indicating that they are itself negatively charged. Actually, cathode rays are electrons. They carry negative charge. So definitely the positive plate will attract the negatively charged electrons, and the deflection was like this, and then the cathode rays strike at the point A and produced fluorescence there. Then J.J Thomson applied magnetic field. He removed the electric field and applied the magnetic field around. This is the red color. This is shown a magnet. That's a north pole. This is the south pole. So when magnetic field was applied at the path of the cathode rays, remember that magnetic field neither attract nor repel the charged particles like cathode rays, but they bend the path of the cathode rays in a curved path. So look at this. For example, these are the cathode rays going straight. When we applied the magnetic field, then the cathode ray bend towards the in this direction and strike at the point C and produce fluorescence there. Then J.J Thomson applied both electric field and magnetic field simultaneously. I mean at the same time. So the electric field tries to bend the particle towards the point A, while the magnetic field tries to bend the cathode rays towards the point C. So actually this magnetic field was rotatable, so he adjusted the magnetic field in such a way that it counterbalanced the effect of the electric field. So the magnetic field was trying to bend the cathode rays towards the point C, while the electric field was trying to bend the cathode rays at the point A. So these two fields cancelled the effect of each other, and the net result was that cathode rays went straight and strike at the point B, as it was in the case when there was no field. So actually here both the electric field and magnetic field cancelled the effect of each other. Then by comparing the strength of both electric field and magnetic field, J.J Thomson determined charge to mass ratio. E is the charge of electron, m is the mass of electron, E by m, this is called charge to mass ratio. So he determined the charge to mass ratio. Actually this is not the charge of electron, but actually he determined the charge to mass ratio, and he applied some mathematical calculations then, and ultimately concluded that charge to mass ratio of electron was equal to 1.7588 and 10 to the raised power 11 coulomb per kg. As we know, charge to mass, charge has the unit coulomb and mass has the unit kilogram. So what is the application of this from this experiment? What we can conclude? This means that if we take 1 kilogram of electron, it will carry so much charge. So 1.7588 and to 10 to the raised power 11 coulomb will be the charge carried by 1 kilogram of electrons. For example, if someone asks that what will be the charge, let's say if I have a discharge tube which carry 100 grams of electrons, so what will be the charge carried by those electrons? Let's say 100 gram is equal to 0.1 kg, and I know that 1 kg of electron carries charge equal to 1.7588 into 10 to the raised power 11. So what will be the charge carried by the 0.1 kg, which is equal to the 100 grams. If you convert the gram into kg, we will get this value. So what will be the charge on 0.1 kg of electron? So this charge is, let's say it is unknown, this is x. By cross multiplication determine the value of x, so we can determine the value of any mass of electrons. In other words, if charge is given, then we can calculate its mass. So this was the J.J Thomson experiment, and he determined the charge to mass ratio, that is E by m of electron, in a modified discharge tube. So this was something about the J.J Thomson experiment. Thank you all.